Welcome students, in this video we will see the design of synchronous 3-bit up counter. We need to design the synchronous 3-bit up counter. The step 1 is determine the number of flip-flops needed. We need to determine how many flip-flops are needed to design the 3-bit up counter. So the 3-bit is available, so the 2 to the power 3 equal to 8, there are 8 states will be there. Capital N equal to 8 states. Because of 3-bit there are 8 combination, that is 0, 0, 0, 0, 0, 1, like that we have 8 states are available. In order to identify the number of flip-flop, the condition given is 2 to the power n greater than or equal to capital N. Capital N is the number of state, small n is the number of flip-flop required. Now we'll substitute 2 to the power 3. So in this problem it is clearly given 3-bit, so definitely we need 3 flip-flop, right? So we'll say directly we'll substitute n equal to 3. 2 to the power 3 greater than or equal to 8. So 2 to the power 8 is nothing but 8. 8 greater than or equal to 8. So this condition is satisfied. Greater than or equal is there. So both the side we have 8. So this condition is satisfied, so that 3 flip-flops are required. Right. So in order to design 3-bit up counter, what we need? 3 flip-flop. From this condition we identify that 3 flip-flops are required. The next step, we need to identify which type of flip-flop we are going to use. Here we are going to use the JK flip-flop. Right, we will use the any type of flip-flop we can use. Here in this problem we will decided to use the JK flip-flop. So the third step is we need to draw the state diagram. The state diagram is nothing but how the 3-bit up counter is going, right? So we decided there are 3 bits are available, so it start from 0, 0, 0, 0, 0, 1, 0, 1, 0, that is 8 combination. This is nothing but 8 combination. Because of 3-bit we are having 8 combination. In this problem it is given up counter. Up counter means it start from 0 and goes up to 111, minimum to maximum. Up counter means from minimum it will go up to maximum. Minimum value is 0, 0, maximum value is 111, right? So this is nothing but state diagram, how the 3 bits are changing step by step. So from 0, 0, 0 it changed to 0, 0, 1, then it will change to 0, 1, 0, then 0, 1, 1, then 1, 0, 0, then 1, 0, 1, 1, 1, 0, finally 1, 1, 1, again it is goes to 0, 0. So it is a up counter, from minimum to maximum it is going. It's called a state diagram, right? Because of 3 variable 3-bit we have 3 combination, there are 8 states are available. The state start from 0, 0 and it will go up to 1, 1, 1, right? Because of up counter. Now we are going to use the JK flip-flop. We will see what is the excitation table of the JK flip-flop. What is excitation table? From the output we can decide what is the input is required. It is just opposite of the truth table. Truth table is from input we can identify the output. Here from the output we are going to check what is the input is required. So this Qn is nothing but current state, present state. Qn plus 1 is next state, right? So present state, next state, J and K is the 2 inputs. For example, current state is 0 and next state also 0. Both are 0 mean what is the input required? JK. J is 0, K may be 0 or 1. That is X. X refers 0 or 1. That means either 0 or 1. Right? So for the current state and next state, both are 0, 0 mean the input what be required? J is 0, K is 0 or 1. Suppose if the current state is 0, if you want to change it into 1, 0 to 1. Current state changed into the next state is 1 means what we need? J is 1, the K may be 0 or 1, right? The third case, so the current state is 1, if you want to change it to the next state into 0, 1 to 0, what is the input required? J may be 0 or 1, K is 1. The second, then the last one, the current state is 1 and final, the next state also we want 1, 1 to 1, there is no change, means the input what we need? J is 0, 1, the K is 0, right? So this is the input required for these 4 different combination of current state and next state. From 0 to 0 mean what we need? The J is 0, K may be 0 or 1. 0 to 1, if you want to change the current state to next state, 0, 1 means J is 1, K may be 0 or 1. From 1 to 0, 0, 1, 1. From 1 to 1, 0, 1, 0. Right? So here the state diagram is available. Here the excitation table for JK flip-flop is available. Now we need to design the excitation table for synchronous counter, 3-bit synchronous counter, right. So what is that, how to find the state diagram? So this is the current position 0 0 0, that is changed to 0 0 1, right. So there are 3 flip flop, we can take it as this is QA, QC, QB, QA. This is QC, QA, QB, QC, like that. There are 3 flip flop, we can name it as ABC. So this is C, B, A, right. See how it is changed. It is changed from 0 0 to 0 0 1. Then it is changed to 0 1 0. So from 0 0 0 to 0 0 1 means what is the input required from this excitation table we need to find. For example, see this 0 is changed to 0. There is no change. This is the flip flop C, B and A. Similarly here the next state QC plus 1, QB plus 1, QA plus 1. See this, the first C flip flop there is no change, right. C 0, both are 0. Both are 0 mean what we need? J is 0, K may be 0 or 1. Similarly the second flip flop B, both are 0, current state and next state. So same thing, J is 0, K is 0 or 1. But the third flip flop A is 0, now it is changed to 1, right. Current state is 0, now changed to 1. So what is the what is the input required for changing from 0 to 1? Is 0 to 1. So the J is 1, K may be 0 or 1, right. Similarly we need to identify, we will go for one more state 0 0 1, right. Now it is changed to 0 1 0. This is the flip flop C. C is from 0 to 0, there is no change, right. What we need? J is 0, K may be 0 or 1. Then second flip flop B changed from 0 to 1, right. If you want to from 0 to 1, what is the input required? J is 1, K may be 0 or 1, right. Similarly the third flip flop A is 1, is now changed to 0, right. Current state is 1, next state is 0. Current state is 1, next state is 0, mean what is the input required? J may be 0 or 1, K is 1, right. Like that we can identify the all different 8 stages. Step by step we need to identify for changing from 0 to 0 or 0 to 1 or 1 to 0, what is the value of J and K for 3 flip flop, right. JA, JB, JC. Similarly KA, KB, KC. We need to identify what is the input to the JK flip flop. That is nothing but excitation table of the synchronous counter. This is excitation table of the JK flip flop, right. Now we will see the excitation table of the synchronous counter, right. This is the present state, what is available in the state diagram 0 0 0, 0 0 1, 0 1 0, nothing but 8-bit combination of binary number. Now this 0 0 0 is changed to 0 0 1, that is this state. From this is the current state, this is the next state. This 0 0 0 is changed to 0 0 1. Again 0 0 1 is changed to 0 1 0. Then it is changed to 0 1 1, right. So this is what is available in the state diagram. This is changed to next state, right. It is from the arrow mark we can easily identify. From 0 1 0 it is changed to 0 1 1, 0 1 0 changed to 0 1 1, right. Finally the 1 1 1 is changed to 0 0. Again 0 0 will change into 0 0 1, like that it will change, right. This is the present state. This simply you can write it as, that is nothing but combination of 8-bit binary number. This is second state. You can see this is 0 0 0. So next number 0 0 1 is coming here, right, because 0 0 is changed to 0 0 1. Then third number is coming here, the second number, second combination, right. So like that this is the next state. I will explain with the state diagram, right. So present state is this state 0 0 0 0 1 0 1 0, like that. What is the next state? From 0 0 the next state is 0 0 1. For 0 0 1 the next state is 0 1 0. For 0 1 0 next state is 0 1 1, right. So that one position is changing. So based on that we wrote the excitation table for the synchronous counter, right. So this is the present state what is available, this is the next state. So for this we need to identify what is the value of JC, KC, the first flip flop, JB, KB, second flip flop, JA, KA, the third flip flop, right, CBA, right. First we will see this QC is 0, QC plus 1 also 0, right, both are 0, means what is the input? The J is 0, the K may be 1 or 0, that is indicated by X, right. Now we'll see the excitation table. See, both are 0 means J is 0, K may be 0 or 1, right. So this table is now implemented in the excitation table of the synchronous counter. Then QB is 0, QP plus 1 also 0. Then same thing. So here 0x, here also 0x, right. The J is 0, K may be 0 or 1, that is indicated by X. The third, 0 and 1. Current state is 0, next state is 1. Changed from 0 to 1 mean what is the input needed? J is 1, K may be 0 or 1, X, right. Similarly, next 0 to 0, same thing, 0x. 0 to 1, what we need? 1x. Then 1 to 0, x1, right. So all what we discussed in the excitation of the JK flip flop, all are implemented. We need to see what is the current state, what is the next state, what is the input required. Like that we need to write all the columns for C flip flop, B flip flop as well as A flip flop, right. I think we are able to understand. From excitation table we are executing. I already explained one column, one example. 0 to 0 means the J and K will be 0 and X. 0 to 0 mean again 0x. Suppose the current state is 0, next state is 1. We want to change 0 means the JK input will be J is 1 and K is 1 or 0, that is indicated by X. Similarly, we can write all the inputs from the excitation table. Right. After implementing this, after completing this excitation table, we need to find the expression for JC, KC, JB, KB, JA and KA from this value by using the K-map reduction technique, right. So there are 8 expression we need to find: JC, KC, JB, KB, JA and KA, right. Now we'll go to the reduction of K-map. So first we will see for JC. So 3 variable K-map: QC, QB, QA. These are all the 3 inputs, right. Current state. From current state only we are going to find the expression for JC, right. So from the tabular column, this marking are given, the cross mark are 1, right. This K-map technique you already know. So we can combine these two cells, so that what we got? QB, QA, right. So this 0 and 1 is cancelled, only we have 1, 1. 1, 1 means QB, QA. JC equal to QB, QA. Similarly for KC, the input is QC, QB, QA. From the tabular column the marking are given. So we can combine these two. Same thing, what is available here? Same thing, 1, 1. 1, 1 means KB, KA, right. So the JC value is QB and QA. KC value also QB, QA. So we need to implement this while designing the synchronous counter, right. Now we'll go to the JB. For JB, right, from the tabular column this marking are given. These two are 1, these 4s are cross mark, right. So we can combine these 4. While combining these 4, what will happen? These two are cancelled. Only we need to verify this second column and third column. In that QB bar both are cancelled. Only we have QA, right. Only the QA is available. QB and QB bar got cancelled. So the JB is nothing but QA. Now we'll go to the KB value. So the KB value, from the tabular column it is marked that 4 cross mark available and 2 ones are there. So we can combine these two cells. If we combine these two cells, these two are cancelled. QC bar and QC cancel. We need to repair only this second column and third column. In that QB and QB bar cancel, only we have QA, right. So JB also QA, KB also QA, right. Now we'll go to the JA. From the tabular column, while marking the JA, what we got? These two cells are 1, these 4 cells are cross mark and these 2 cells are 1, right. So we can combine all 8 cells, all 8 cells are combined. This is called a don't care condition. While grouping we can take the don't care condition, right. So if you take all these 8 cells, these are all cancelled, everything cancelled, only we have JA equal to 1, right. The input to the A flip flop, J flip flop, the A type is 1. Now we'll go to the KA. What is the input for KA? So for KA, from the tabular column it is marked as these 2 are cross mark, don't care condition, these 4 are 1 and last column also don't care condition. So here also we can group all 4 cells, all 8 cells, right? So that what we got, Ka equal to 1, right? Now we got the value of JC, KC, JB, KB, JA and KA, right? JC and KC is nothing but QB, QA, right? JB and KB is nothing but QA. JA and KA is 1, right? So based on that, we need to design the 3-bit up counter, right? So we already discussed that there are 3 flip-flops are required, A, B, C, 3 flip-flop of JK type, JK flip-flop, right? So this is the first flip-flop, JA, KA, JB, KB, JC, KC, right? 3 flip-flops are available. It's a clock pulse. The clock pulse is given to all 3 flip-flop. So this is the output, QA, QA bar, QB, QB bar, QC, QC bar, right? We need to give the input now. What is the input? JA and KA. See this KA. KA and JA is 1. So 1 is given for both JA and KA. What is the input for JB and KB? That is QA. So here the QA is available directly connected to JB and tapping is taken, that is connected to KB also, right? So the JB and KB value is QA, right? What about this JC? JC is nothing but JC and KC, both are QA and QB, right? We need to multiply QA and QB, so that we are using one AND gate. So this is KB, this is KA. So both are connected. Due to AND gate, it will multiply QA and QB. So output of this AND gate is given to JC as well as KC, right? So all 6 inputs are given. JA and KA is 1. Then JB and KB is QA. JC and KC is QA into QB, right? Now we design the 3-bit up counter, so that it will generate the 3-bit up counter, that is from 000 to 111 in a order, right? So in this video we discuss about the design of synchronous 3-bit up counter. Thank you for listening. Welcome students, in this video we will see the design of synchronous mod 6 counter, right? We need to design the synchronous counter mod 6. There are 6 states. Mod 6 means there is a 6 states are available, right? So we need to identify what is the type of flip-flop and how many number of flip-flops needed. So the step 1 is determine the number of flip-flops needed. So the mod 6 is there, so that n equal to 6. There are 6 states will be there. Number of states will be 6. So from this condition, 2 to the power n greater than or equal to n, right? This n is nothing but state. This small n is nothing but number of the flip-flops required. So the 6 is there. So we'll try with the 3. 2 to the power 3 greater than or equal to n. So 2 to the power 3 greater than or equal to 6. The n is 6. So the 8 is greater than or equal to 6. So this condition is satisfied, right? So we need 3 flip-flop. 3 flip-flops are needed for this for these 6 states, right? So normally there will be 8 states will be there. The 3 flip-flop mean the 000 up to 111, there are 3 bits will be available. So here only 6 states are available. So the 7 and 8 last 2 states are taken as a don't care condition. That is taken as don't care condition, right? Now we identify there are 3 flip-flops are needed. The second step is type of flip-flop. Here we are going to use the JK flip-flop. We can use any type of flip-flop, but in this problem it is solved with the JK flip-flop. The third one is we need to draw the state diagram, right? We need to state the state diagram. So in this given there are 6, mod 6 is there, so that there are 6 states, 000, 001. That is nothing but 3-bit binary number, combination of 8. In that there is 6 is available. This 7 and 8, that is the 6 and 7 is the don't care condition. Here from 0 to 5 available, 6 and 7 is don't care condition, right? So how it is changes, it's normal binary number, 3-bit binary number, 0002 001, then 010, 011, 100, 101, right? So there are 6 states are available. Again 101 is changed to 000, right? So from the state diagram what we are understanding, so this is the current state. This is the next state. We are going to use the flip-flop. See this 000 means we are going to use the 3 flip-flop. You can take this is the flip-flop C, B and A, right? For the C flip-flop, the state changed from 0 to 0. B changed from 0 to 0. C changed from 0 to 1, right? So the B and C there is no change. Here also 0, here also 0. For the A flip flop changed from 0 to 1. For this we need to say what is the excitation table. What is the excitation table of the JK flip flop, so that we can decide the input to the JK flip flop. So this excitation table is nothing but we are from the output, that is from current state and next state, we are going to identify what is the input required, what is the input J and K is required, that is the excitation table. Truth table means from input we can identify the output. Here from output we are identifying what is the input required. For example, the current state and next state both are 0, there is no change, mean what we need J is 0, K may be 0 or 1, that is X. Suppose the current state is 0, next state is 1, changed from 0 to 1. What we need J equal to 1, K may be 0 or 1, X. Similarly 1 to 0, current state is 1, next state is 0, means what we need J is X and K is 1. If both are 1, current state and next state, what we need J may be X 0 or 1, K is 0, right. So from this we need to identify what is the input to the J and K. For example, see this 0 to 0, there is no change. 0 to 0 means what we need J is 0, K may be X. For the second flip flop B also 0 to 0, so J is 0, K is X. The third flip flop A changed from 0 to 1, that is this 0 to 1. So what we need, the input to the J is 1, the K is X, right. So this is the next step, excitation table of the counter we need to decide from this excitation table. By referring this state diagram and excitation table, we can frame the excitation table of the counter, right. We see one more, here also 0 to 0 means 0 and X. Here 0 to 1 changed from 0 to 1, 0 to 1 means J is 1, K is X. Then 1 to 0, the current state is 1, next state is 0, 1 to 0, current state is 1, now it is changed to 0, means what we need, the J may be X and K is 1, right. So like that we can identify all, right. So start from 0, it goes up to 6 combination, again it will enter to 0, the 6th, 7th and 8th, that is 6th and 7th position is don't care condition, right. Now we'll go to the excitation table of the counter, right. Now we'll refer both excitation table, state diagram and excitation table of K flip flop. So this is CBA, current state of the C flip flop, B flip flop, A flip flop. QC plus 1, QB plus 1, QA plus 1, next state of the C flip flop, B flip flop and A flip flop. This JCKC, that is the input to the C flip flop. JBKB, input to the B flip flop. JAKA, input to the A flip flop, right. Now this only we are going to identify, right. So first is 0 0 0, right, that is changed from 0 0 1. The current state is 0 0, it will change to 0 0 1, right. Second is 0 0 1 is changed to 0 1 0, like that we need to write, right. Current state, next state from the diagram, 0 0 0 to 0 0 1, 0 0 1 to 0 1 0, right, like that we need to write. So that is very simple. The first column we can write as it is, all 8 combination. The second is nothing but 0 0 is changed to 0 0 1, so this 0 0 1 will come here. Then 0 0 1 changed to 0 1 0, this will come here, right. So the last 2 digit is don't care condition, right, because it is a 5 counter, 6 counter, 7 and 8 is considered as X, don't care conditions. Now we'll refer this, how to find the input of the 3 flip flops, right. I think you are able to understand. This is current state and next state, this is the current state, next state, this is the current state, next state, current state, next state, like that we need to write. That is first column we can write as it is, second column you have to write like this is the first, because 0 0 changed to 0 0 1, right. So this is the first combination, second 3 4, again it will go to 0 0, right. Now we'll see this is 0, next state also 0, both are 0, mean what is that, J is 0, K is 1, K is X, see this J is 0, K is X. Similarly B, that also 0 0, that means J is 0, K is X. Then third flip flop A, 0 to 1, 0 to 1 means the J is 1, K is X, so J is 1 and K is X, right. So this only we are identifying from this excitation table. We can go for one more, 0 0 mean again it is 0 X, 0 to 1, 0 to 1 means 1 X, 1x. 1 to 0. 1 to 0 mean x into 1. 1 to 0, here 1 to 0, here x into 1. The input is x into 1. Like that we can identify for all 6 combination. All 6 combination of the this binary number. We can identify what is the input to the C flip-flop, B flip-flop and A flip-flop. These last 2 are don't care condition. Only 6 combination available, 7th and 8th is don't care condition. Right. Now we got the value of JC and KC, the flip-flop C, flip-flop B and A. From this we need to identify what is the expression for JC and KC by using the K-map reduction. Similarly JB, KB using the K-map reduction, JA, KA from the K-map reduction, right. Now we'll go for the K-map reduction in order to identify the expression for this 6 combination. So for JC, the inputs are QC, QB, QA, the current states. The current states are the input, the output is expression for the C flip-flop J. Similarly, we can go for K, right. So the input is QC, QB, QA. QC having 2 combination, QC bar, QC. QB, QA 2, so that 4 combinations are available. QB bar, QA bar, QB bar, QA, QB, QA, QB, QA bar. That is 0, 0, 0, 1, 1, 1, 1, 0. Right. So from the tabular column it is marked. These 4 are don't care condition. This is 1. So we can combine these 2 cells. If we combine these 2 cells, these 2 row got cancelled. Only we have to refer this. That is KB into KA. So the expression for JC is KB into KA. Similarly, we can go for KC. What is the expression for KC? Right. Here there are 1, 2, 3, 4, 5, 6. 6 don't care condition available. That is, and only 1 is there. This is not only don't care condition. That is, the input to the JC may be 0 or 1. So based on that we have cross mark. So we can combine these 4 cell. While combining this 2 column, these 2 rows got cancelled. Only we need to refer the second and third column. So QB bar and QB cancel. Only QA is available in both. So that KC equal to QA. The input to the KC equal to QA. Now we'll go to JB. The expression for JB. Right. So here only this is 1, remainings are cross mark. So we can combine these 2. Right. So while combining these 2, what we got? So this we have to refer this QC bar here, QB bar cancel, only QA. So QC bar QA, right. And also we can combine all, so that the JB equal to 1 also, that is also correct. This is another case, only we combine these 2, right. QC bar into QA. Then we'll go for KB. For KB, there also this is the only one, others are cross mark. So these 4 are combined together. Here also we can combine all 8, but here only this 4 is combined. So what we got? QA. These 2 are cancelled, QB bar cancel, only QA is available. KB equal to QA, right. Now we'll see the JA and KA. So the small correction in the JB, right, the JB not having the all 8 cells are available. So these 3 are zeros, only this is 1, the remaining 4 are cross mark, don't care condition. So that we are combining only these 2. There is no other possibilities available, right. These 3 are 0, not X mark. Previously I marked as X, it is not correct. These are all 0. So that we are not able to combine all 8 cells. So that we got QC bar and QA. Similarly KB also, this is 0. So that we are not able to combine all 8 cells. Only we can combine this 4 cell. So that we got KB also, KB is QA, right. So it's a small correction. So here this is 0. Otherwise we can make it as all 8 cell we can combine. So that because of 0 we are not able to combine. Now we'll go to JA and KA. For JA, here all are covered, right. These 3 ones and remaining are cross mark. So that we can combine all 8 cells. So that we got JA equal to 1. Similarly KA also all cells are covered. These 4 are ones. These 4 are cross mark. So that we can cover all 8 cells. We got KA equal to 1. So we got the value of expression for JA, KA, JB, KB, JC and KC. So from that we can design the counter, mod 6 counter, right. So we already discussed there are 3 flip-flops are required. Flip-flop A, B, C. Right. So this is JA, KA, JB, KB, JC, KC. Input to the flip-flop. Outputs are QA, QA bar, QB, QB bar, QC, QC bar. So this is the clock pulse. So the clock pulse is given to all 3 flip-flops. Right. Now we need to see what is the input. For JA and KA, the input is 1. 1 is given to JA and KA. What is the input to the JB? It is QA into QC. Right? QA it is available here. QA is directly connected. QC bar where it is available here, available here. So QC bar is connected to this AND gate. This is AND gate. One input is QA, another input is QC bar. So the AND gate will multiply this so that QA into QC bar is given to the JB. Right. What is that KB? What is the expression for KB? Only QA. Right. This QA is given to KB. Right. What is the expression for JC? JC is QB into QA. These are all what we discussed from the K map. These expressions are available in the K map. QB into QA. The QB is available here. We have one AND gate. QB is available. Where is QA? QA is available here. This is QA. Right? QA is connected. So QB, QA multiplied QB into QA, that is given to JC. Right? What is KC? KC input is QA. Right? This QA is available here. That is given to KC also and as well as this AND gate. Right? Now the input is given to all 3 flip-flops so that we can get the mod 6, the counter, synchronous mod 6 counter. The design was completed. So in this video we discuss about the design of synchronous mod 6 counter. Thank you for listening. Welcome student. In this video we will see the design of synchronous mod 6 gray counter. Right? So this we need to find the gray counter. So first we need to see what is how to convert the binary to gray. Right? So this is the binary number. 0 mod 6 is there, so definitely there will be 8 combination. 3 bit will be there. So we can take 3 bit binary number 00, 001, 010, like that it will go up to 111. Right. So this binary number should be converted into gray code. How to convert this binary to gray is available here. 001 means we need how to find the gray. So 0 is written as it is. The first 0 written as it is. The first and second 0 is we find the XOR gate. The output of XOR. Right. What is the XOR gate is available here. A, B, 2 inputs and output Y. 0 mean it will give 0. 1 mean 1. 10 mean 1. 1 mean 0. That is both the inputs are same mean it will give 0. Both the inputs are same mean it will give 0. Both are different mean it will give 1. Right. That is the nature of the XOR gate. Right. From 0 to 0 mean 0. 0 into 1. 0 and 1 XOR mean it will give 1. Right. First digit written as it is. First and second digit we need to find XOR. Both are same mean it will give 0. Both are different mean it will give 1. We will go for one more combination 101. So 1 is written as it is. This 1 and 0 XOR both are different means it will give 1. Similarly 0 and 1 both are different mean it will give 1. Right. For 001 binary number the gray code is 001. 101 means 111. Right. We are able to understand. The 0 is written as it is. First digit is written as it is. The second digit is nothing but we need to find the XOR of first and second. That is this both are equal mean 0 only. Again second and third both are different mean it will give 1 based on the tabular column. Right. So based on that the binary number is converted into gray. Right. 00 means 000. 001 001. 010 011. 011 means 010. 100 means 110. 101 means 111. Last 2 are don't care condition because only 6 is given. Right. So based on this calculation these are all converted. Now we need to refer this gray code. We are going to design the converter only for this gray code with 6 combination. Last 2 are the don't care condition. Right. Now we will see the state diagram. Now we have to refer this. The state diagram is nothing but referring this 0002 001. Now we will see the state diagram. See this 002 001, 0012 011, then 010, then 110, then 111, again 00. right? So this is the state diagram. So what we calculated the binary code, it is a state diagram. Another two are the don't care condition, right? So from this we can identify there are 3 flip-flops are required. We can select the T flip-flop. We can select the T flip-flop, right? Now we need to identify the excitation for table for the counter. So first we will see the excitation table of the T flip-flop. What is the T flip-flop? The excitation table means we are identifying what is the input required for the given output. For example, this is the current state and next state. If the current state is also 0, next state is also 0, mean what is the input to the T flip-flop is nothing but 0. That is called excitation table. Similarly, the current state is 1, next state is also 1, mean the input to the T flip-flop is 0. That is, there is no change, mean the T input will be 0. Suppose 0 to 1, current state changed to 1 or current state changed from 1 to 0, mean the flip-flop, that input to the T flip-flop is 1, right? So there is no change in the state, means 0. Any change in the state 0 to 1 or 1 to 0, mean it is 1 1. That is the nature of the T flip-flop, right? Now we will find the excitation table for the this counter. So this is the present state, this is the next state. What is present state? These 6 gray codes 0 0 0 0 1 0 1 1 0 1 0, what we discussed in the state diagram, the 6 are available. For 0 0 0, what is the next state? 0 0 1. For 0 0 1, the next state is 0 1 1, right? We will refer the state diagram. See this, for 0 0, the next state is 0 0 1. For 0 0 1, the next state is 0 1 1. For 0 1 1, the next state is 0 1 0, right? So all 6 are written as a current state. The next state is written in the second column, the NS. NS is nothing but start from here, 0 0 1. For this is the next state, so that 0 0 1, then 0 1 1, right? So all 6 are written as a present state. The next state, that is the second number, is start from second number, we wrote as a next state, right? Now we need to identify the QC and QC1 both are 0. What is the input to the T flip-flop? That is nothing but the excitation table of the counter, right? So there are 3 flip-flop available, CBA, right? Flip-flop C, flip-flop B and A. So QC, QB, QA is nothing but the current state of the 3 flip-flop. QC1, QB1, QA1 is nothing but next state of the flip-flop. For that we need to identify what is the input to the T flip-flop, C, B and A. There are 3 flip-flops, flip-flop C, B, A, right? For 0 0, there is no change, means we already told that 0 0 means the T flip-flop will be 0. Here also 0 0, this is B, and QB means current state, QB1 means next state. So the QB is also 0, QB1 also 0, means there is no change. QA is 0, but QA plus 1 is 1. There is change. 0 to 1 is changed, mean the TA will be 1. That is given here. From 0 to 1 mean the T value will be 1. From 1 to 0 also T value is 1. Now we will see one more. For 0 0, there is no change. So it is input is 0. This also changed from 0 to 1. So the input will be 1. Here 1 to 1. There is no change. Current state and next state. So that it is 0. So like that we can frame the entire table for the present state and next state. What is the input to the 3 flip-flop C, B and A. Now we need to find the expression for TC, TB and TA by using the K-map reduction. Now we'll go to the K-map reduction. For TC, the third flip-flop, the input for TC, the expression for TC, the inputs are QC, QB, QA. The 3 current states. The current state of the 3 flip-flop is the input. The QC having 2 combination, QC bar and QC. QB, QA, 2 bit is there, so the 4 combinations are available. QB bar, QA bar, QB bar, QA, QB, QA, QB and QA bar. That is 0 0, 0 1, 1 1, 1 0. Right. Now we can go for the simplification. Right. So there's only the 2 ones are available and 2 the don't care conditions are available, remainings are 0. So we can combine these 2 and this one is available individually. So by simplifying that, what we got, while combining these 2 we have to refer this QC and these 2, QB bar and QB cancel, only QA. So QC into QA. While referring this, we have to refer this QC bar and QB QA bar, right? So QC bar, QA bar, QB, right? So the expression for TC is QA into QC plus QA bar, QB and QC into QC. Similarly, we can go for TB, the expression for TB, second flip-flop. So these two are ones, these two are zero, yeah, cross mark, others are 0. So these two are combined and these two are also combined. So while combining these two, we have to refer this QC. We have to refer these two. This QB and QB bar cancel, QA. So QC into QA, QC into QA. While referring these two cell, these are cancelled. Only we have QB bar and QA, QB bar and QA. So the expression for TB is QA, QB bar plus QA into QC. Similarly, we can go for TA, the expression for third flip-flop. So these 1, 2, 3, 4, 4 ones are available, 2 cross mark available and these two are 0. So we can combine these 4 cell, these 2 cell and these 2 cell. While combining these 4, we have to refer this QC, all are cancelled, only we have QC. While combining these two are cancelled, we have QB bar, QA bar, QB bar, QA bar. While combining these two, these are all cancelled, we have QB and QA, right? Now we got the expression for TC, TB and TA. From that we can design the T flip-flop. So we already discussed there are 3 flip-flops are needed. So this is the flip-flop A, B and C. This is the clock pulse, right? So the clock pulse is available. The clock pulse is given to all 3 flip-flop. The output is QA, QA bar, QB, QB bar, QC, QC bar, right? So for TA, what is the input to the TA? What we discuss in the K map is nothing but accordingly it is connected. The TA is nothing but QA bar, QB bar plus QA, QB into plus QC, right? There are three expressions are available that is connected here. These are all connected accordingly what we got as a TA. Similarly TB, right? These two AND gates, so it will multiply, then it is added together, right? The TB what we got is QA into QB bar plus QA into QC, right? So accordingly it is connected. QA, QB bar, QA into QC are connected, both are multiplied, then it is added. Similarly TC, TC what we have? QA, QC plus QA bar, QB, QC bar. So accordingly these two are connected, right? So we can see from the diagram it is clearly we can identify that, then it is given to the TC, right? So the input is given to TA, TB, TC according to the reduction in the K map. What be the expression what we got in the K map accordingly connected. So this flip-flop will generate the 6-bit gray code. It will generate the 6-bit gray code, right? So in this video we discuss about the mod 6 gray counter, the binary to convert it into gray, so it will generate the gray code directly. Thank you for listening.